Welcome, everyone. My name is Sylvie Nadeau. I am full professor and director of the Applied Human Factors Lab at the Mechanical Engineering Department at École de Technologie Supérieure in Montreal, Canada. I'm also director of the master's program in Occupational Health and Safety Risk Engineering and faculty representative at École de Technologie Supérieure in Montreal. I'm member of the Scientific Committee of the Intelligent Cyber Value Chain Network in Canada and co-chair of the IEA Resilience Engineering Technical Committee. We are pleased to have you with us to share this third presentation of a series of 4 on systemic methods in complex and digitalized manufacturing, a webinar series organized by the Resilience Engineering Technical Committee of the International Ergonomics Association. Today, Dr. Alimeh Mofidi Naini will share her collaborative work on FRAM-STPA model, a case study of an Industry 4.0 plant using a digital glove. This presentation is based on an earlier journal paper published in the Robotics and Computer Integrated Manufacturing Journal and funded by the Natural Sciences and Engineering Research Council of Canada. Before we kick things up, I have a few housekeeping items. We are expecting this webinar to last about 60 minutes. IEA is recording this webinar and it will be made freely available on the IEA website. We encourage you to send questions and comments throughout the presentation using the Q&A feature and use the chat feature for the administrative issues. I'll be managing the Q&A and we have time reserved at the end for answering your questions. I will now give you a few details about our speaker. Dr. Alimeh Mofidi holds a Doctor of Philosophy degree from École de Technologie Supérieure, where her research focused on occupational health and safety and operational risks in Industry 4. She also earned a master's degree in business administration from Key and Tuzi University of Technology and a bachelor's degree in industrial engineering from Isfahan University of Technology in Iran. In addition to her academic achievements, Dr. Mofidi has published research in the Robotics and Computer Integrated Manufacturing, CIRP Journal of Manufacturing Science and Technology, and African Journal of Business Management. She has served as a lecturer in both Iran and Canada. In her professional career, Dr. Mofidi is currently a product specialist and product manager at Siemens in Canada, with over 2 years of experience in project oversight and project specification management in that organization. She also brings 9 years of expertise from her roles as quality assurance expert and manager, production and project control expert and manager, and project risk evaluation expert in Iran's manufacturing industry. Welcome, Alimeh. I'll let you take it from here. Everything
Hello,
is
everyone. Am I audible now?
it's fine.
Hello,
You
everyone.
can start.
Thank you. Hello, everyone. This is Alimeh Mofidi. I'm very pleased to have to be here and share the results of my PhD studies with you. Today, I'm going to present a case study of Industry 4.0 plant using a digital glove. This study has been done during my PhD study, and here I will present the preliminary results I published in robotic journal. So let's have an overview of the items that will be presented in this presentation. First, we will provide you an introduction of data gloves and use of these data gloves in different areas. Following, I will explain the methodology that we use for this study and why we chose those methodology. After, the result of the application of the methodology and case study will be discussed. And at the end, we will discuss and conclude based on the results that we study. And at the end, I will be pleased to answer the questions that you might have for the presentation. So first, let's look at data gloves and see what is data gloves. Data gloves are specific tools which we name them wearables that have some sensors, mostly internal sensors. These sensors can be magnetic, optic, ultrasonic, or inertial. And they can track the movement of hands and fingers, and they can provide feedback for the users of these gloves. This feedback can be haptic, tactile, resistance, or vibration. Different studies have shown that the data gloves have been used in different sectors. For example, they have been used for information visualization, or they have been used for robotics to train a robot to do the jobs. They also have been used in art and entertainment, where you might be familiar with augmented reality, and you have seen a few applications of this. It also has been used for understanding sign languages, where people cannot hear, so this can transfer the movement of fingers and hand to text, and the people can understand what we are saying. And it also has been used in medicine and healthcare. And the final sector that has been used is design and manufacturing. In this study, we're focusing on manufacturing, and the scope of the project will be in assembly area. To analyze the risk of introduction of data gloves to a manufacturing system, we designed two realistic case studies. In this case studies, data gloves is introduced to a Assembly 4.0 context, and from there we will use approaches to analyze the risk of introduction of such emerging technology to Assembly 4.0. I will provide an explanation of the case studies and how different components of the case study work together. So we will have a better idea of how this kind of risk might happen during the operations. The first case study looks for the use of data gloves in assembling connectors for a car manufacturing. As you can see in the left corner down, in car manufacturing, there are some connectors that needs to get connected to each other. For these connections, the assemblers need to put male and female part to each other and then push the button on top of it. When they are assembled correctly, they provide a vibration and a click noise for the worker, so it shows that the assembly has been done correctly. During that time, the worker's hand might get numb, and it will have less sensitivity to this to the vibration, and also the assembler might not realize the noise of the click in the area of the assembly, that there are a lot of other noises in the area. So we introduced data gloves that can help the worker to make sure that the assembly of the connectors are done properly. The worker wears the data gloves and then push the button. If the assembly has been done correctly, from the sensors that we have in the data gloves, it can give a signal like a green light on the gloves that shows the worker that assembly is done correctly. Then the worker will put the connectors on the conveyor, and the conveyor is also equipped with some sensors to align the speed of the conveyor with the worker's speed. So the other groups of assemblers that are waiting for the connectors to receive to their station and work on the other part of this assembly can get it according to the assembler's speed. So we will have a constant flow of the material that comes to the station and go out from the other station. In the system that we're explaining, we also have other components of the system. The worker is interaction with his colleague, with the supervisor, and with the technical support that can help to provide calibration for the data gloves, and also if there is any technical issue. The gloves is also connected to an area that receives and processes the data. This data will be used by the worker and by the upper level of the system, including the material planning, including production planning, including training, and the other resource management. The second case study, we also use data gloves with the help of smart glasses for assembly island. Let's see what is assembly island and what is the benefit of the use of data gloves in such assembly islands. We use assembly islands when there is a big and giant product that needs to be assembled, like aircrafts, and we cannot move the product easily. So the assemblers will stay in a fixed point, and the items will be transferred to them from different places. Usually these giant products are very complex. They have a lot of components that needs to be assembled to each other, and especially for the countries that are extended and they are very big, it will be very difficult to have the technical support, the supervision, and everything provided at the same time for different islands. So we introduced data gloves with the help of the smart glasses to assemblers who work in this assembly island. The worker goes to assembly island, wears the data gloves and the smart glasses. So different components are in front of the worker, and the worker will take the components with his hand. The data glove takes the dimension of the item or the specification of the item, and then sends the information to data center. It will be processed, and the location of the assembly will be shown in the display of the smart gloves for the worker. So he will need less helps from the supervisor or technical to help them with the assembly of the product. At the same time, if there is a problem with the assembly or there are some technical issues, the worker can communicate with the technical support and show the assembly desk to the technical support with the smart glasses, and then he can take the components that are supposed to get assembled with his hand, and then technical support from the data that is sending to the receiving area can process it and let the worker knows how to proceed with the rest of the assembly process. In the system, we can see that we have different islands that are connected to each other, connected to a supervisor, and connected to technical support. They are also sending information to receiving and processing area, and this information will provide feedback for the workers in different islands, and also for the supporting system components such as training, such as production planning and resource management. So now we know that we have used data gloves for two different assembly, and now we will see what will be the operational and OHS risk concerning of introduction of this data gloves to assembly 4.0 context. For this, we need to first find what will be the appropriate methodology for analysis of risk of this context. Within the time, we have seen that the methodologies that have been used for risk analysis have been developed, and from FMEA, we're going to use methods that are more systemic and not technical, because we're facing systems that are that includes humans, organizations, and different parts of the system. So from there, we can say that We can say that in the system that we are analyzing, there are two main components that we need to consider. First, data gloves, smart glasses, tools and materials, and other components that we call them technical component of the system. And at the other hand, we have humans, organizations that work with this and they have interactions with the hardware or the system. So this system the system that we are analyzing and we're studying is called a socio-technical system. And from the previous slide, we could see that the technical methods like FMEA will not provide all the information when we have a system, when we have to look at the case study and the analysis from a systemic perspective. Here also, there is a study that shows that the different methods of risk analysis can be categorized in 4 categories, and they are based on the coupling of the components of the system and the description of the system. The more they are interactable, they goes to the systemic view, and when the couplings are a lot, we consider them as complex system. Here at left, you can see that assembly lines that were located in the third section, where the coupling of the component of the system was loose and they were not very in interaction with each other. With the introduction of the data gloves and Industry 4.0, the couplings of different components are getting tighter and they will be less traceable. So they will go from the quarter 3 to quarter 2, where STAMP and FRAM are suggested method for risk analysis for this context. We also find that there are limited studies that have investigated the OHS and operational risk of the application of wearables as emerging technology in the manufacturing. And as explained earlier, the technical and classical method cannot provide a holistic view to understand these systems properly. So we decided to go with the analysis of the system with the use of two systemic approach, FRAM and STAMP. The research that have been done in different steps. The first step, we designed realistic case studies that I explained the case study to you. In the next step, we applied FRAM on both case studies, and we try to have a good understanding of the components of the system, how the variability can affect the system. And in the next step, we applied STAMP-STPA on our system to see what are the controllers, what was the unsafe actions, and then we compared the result of application of these two methods on our case studies. And from the comparison, we concluded a new risk management approach. Let's see what will be the result of the application of FRAM on our case studies. FRAM is a systemic perspective that looks at the system look at the system, and it considers the components of the system from the function that they are doing. And this function will be affected by variabilities, and they provide output and input for the system. From the system that the case study that we introduced earlier, we could analyze the system in different functions, including human functions, technical functions, and organizational functions. Technical functions are the one that have been identified in yellow, organizational in green, and human in blue. So we can see that both of the case studies include three main functions: human, organization, and technical, and at the same time, we were able to analyze them in different layers of the Industry 4.0 system, which is a manufacturing layer or assembly layer, perception, interaction, and cognition layer, and service layer. And this function, we try to map them according to their function in this different service and different layers of the Industry 4.0. Application of FRAM on our case studies, we were able to provide a map of functions and their input and output and interaction with each other. So it provides, we could say that it provides a good understanding and explanation of the components of the system. With analyzing the system with FRAM, we could understand the outcomes that are non-causal, emergent, and they might happen considering the variability, and the possible outcomes. And when we look at the system from the perspective of variability, it helps to understand and ensure that the safe design have been considered. And this variability can help us to understand how the interaction of the main three components, which we discussed, human, organization, and technical, can affect each other and affect different levels of the system. And FRAM can tell us what can go wrong and what can go right. We find out that FRAM is a very time-consuming method, and it requires a thorough knowledge to the system and also to the methodology to be applied on different methods. So it's kind of, especially when the number of the functions go up, it requires a considerable amount of time to analyze the system with different variability that we have identified. In the next step, as we explained earlier, we applied STPA on our two case studies. So we defined the components of the system, and we defined controllers and feedbacks, and then from there we could identify what are unsafe control actions and what can be done to improve it. As you can see, STPA can look at the system from the perspective of unsafe control actions, and application of this method could help in especially in the early phase of the concept design, as we can see what are the unsafe control actions, and then we can find some improvement for these unsafe control actions. And this recommendation is very helpful for the system design as well as the wearable designs that are both in the early stage of designing. I would say STPA, as STPA mostly deals with accident or safety scenarios, it looks at what can go wrong and looks at accidents, and it is weaker compared to FRAM for providing a generalized understanding of the system behavior. In the next step, we provided a comparison of the FRAM and STAMP-STPA on the case studies. With the result that we got from the application of these two methods, we could find some similarities and some differences with these applications. As similarities, we can tell that both FRAM and STPA are systemic views and provide systemic understanding of the system. And they both require a considerable amount of time for the analysis. They are useful for finding hazards and finding what can go wrong, and they are good approaches and appropriate approaches for risk analysis in Assembly 4.0, and they are helpful for improving a system and technology design. But as differences that we find out with the application of these two methods on our case studies, we find out that FRAM can provide a comprehensive description of the functions and the effect of their interaction with each other, while STPA provide detailed analysis of the system component from the perspective of unsafe control actions. FRAM is useful for identifying functions and their variabilities, while STPA can look at the system and their feedback and provides recommendation for unsafe control actions. FRAM is very precise and very detail oriented for the behavior of the system, while STPA is precise for the providing unsafe actions, while FRAM can tell us both what can go wrong and what can go right. Sorry. So, and also we could say that FRAM provide the results of the FRAM application are mostly descriptive and they are unstructured, while for STPA application we have a structured documenting of risk analysis, and they can be documented in a structured format, and for sure they can be referred later much easier because they are structured, not descriptive. These are the these are the similarities and differences that we found during the application of these two methods on our case studies. From this, we decided to take benefit of both FRAM and STPA and provide an integrated FRAM-STPA method. Why we decided to use this? Because we realized that if we use FRAM and STPA together, we can use the FRAM for providing a macro analysis of the system, look at different functions and the variability of the system, and what can go wrong, what can go right. And at the same time, we can use STPA to provide a micro analysis of the system and have some recommendations for unsafe control actions that we know that they might lead to a hazard, and provide a structured analysis. This structured analysis is very helpful in the early stage of the concept design, as it can help to prevent unsafe control actions. So, how this integrated FRAM-STPA model works? For this new approach, we first provide a FRAM model of the studied system, as we did earlier. And then we identify the most variable functions by quantifying the functions through Monte Carlo simulation. We did the Monte Carlo simulation application, and for the first case study, we found out that assembling connectors and receiving data are the most variable functions in the analyzed system. And also for case study 2, assembling the product and transportation management are the most variable functions. Then we go inside of the function and we apply STPA analysis to see what are the unsafe control actions, to have some recommendations for improving them. So we present constraints, controls, and feedback inside the function, and then we will provide preventive recommendations for these most variable functions that have been identified through the application of FRAM. As discussed for the first case study, we realized that assembling connectors and receiving data are the most variable. Then we tried to find out in assembling connectors, what are the components that work together? which here is worker and data gloves, and what are the controls and what are the feedbacks, and this control and feedbacks goes to which variability that we have for this function. For example, you see that here for control variability, we have the most feedback that comes to one of the components of this function, and we have also some precision that as a variability that goes to data gloves. So we can find which variables are the most variables that we need to look at, and at the same time, what are the unsafe control actions from this. So we will work on it to make sure that we have less unsafe control actions. The same application for receiving data. We find out what are the components that we have in this function, and then we try to provide control actions, feedbacks, and these control actions and feedbacks are which kind of feedbacks or control actions from the perspective of FRAM, if they are control, time, resource, precision, input or output. And we did the same application for the second case study, which the most variable functions were assembling the product and transportation management. As you can see, there are a lot of feedback and control that goes to control, which shows that control variability is the most variable, is the variability that will affect the system a lot and cause a lot of and might cause unsafe control actions for our case study. At the end, we validate the result through the triangulation of the result. The first application, which was FRAM application result, was published in Robotic and Manufacturing Journal, published in 2022. And the second application, that was the application of STPA in our case studies, was published in 2021. And then the combination of these two methods and proposing a new approach, which is integrated as FRAM-STPA, was published in 2023. And this triangulation showed that the result that we could provide from the application of FRAM-STPA and integrated method are aligned with each other, and they are valid for these case studies. So from this application, we could say that the integrated method that we have proposed for our case study can provide systemic perspective to the system. It can provide at the same time macro and micro analysis of the system once we use FRAM and STPA for our case studies, meaning that we use FRAM for providing a macro analysis of the system, then we use STPA to zoom in the function and do micro analysis of the system. If we want to use both methods at the same time for all functions and components, it will be more time consuming. So when we use FRAM and then we go only for most variable function and zoom in through the application of STPA, it will require less time. At the same time, we're sure that we have identified the most variable functions. And these two applications are complementary to each other. So their application can provide a holistic and precise perspective to the system. And STPA can help us to highlight the safety control actions that needs to be considered during the designing, and FRAM can help to find what are the safety controls that we need to consider to have less variability in the system. For the limitation of this method, we could say that as we need to do quantitative analysis to find out what is the most variable function, and we are in the preliminary stages of technology readiness level of data gloves. there are limited data regarding real data regarding their applications. So it is very it is very dependent on the analyst elicitation for making it quantitative. Therefore, we would say that there is still the need for more studies and lab experiment to have more real data and less dependent on analysis elicitation. The application of integrated method requires the knowledge of both disciplines and the holistic understanding of manufacturing and different components of the system. And as it is very, it is very, as it requires a good and comprehensive knowledge of the system, it is very resource demanding for computing, quantification, and data acquisition. What is the implication of this method and what are the areas for improvement? As discussed earlier, data gloves are in early stage of technology readiness level. So these kind of studies can help the designers for wearables, especially data gloves, and for the designers of the Assembly 4.0 context to improve OHS and operational concerns in their designing. And for sure, we need more further real-world application in several contexts to have more real data for the use of this new technologies in manufacturing. Thank you for your attention. If there is any question, I'm more than happy to answer.
Thank you, Ali May. Thank you very much. So we do have a questions in the Q&A. How did you assign control action on the one hand and feedback on the other hand to the internal STPA analysis within a FRAM function? Did you, for example, treat some FRAM aspects like control always as a control action and other aspects always as a feedback? How did you approach this?
For the application of STPA inside of FRAM, we looked at the type of the control action and we looked at how it will affect the system. If it's a control or feedback from the perspective of control, we assigned it to control. If it's a control from the perspective of time or precision, we assigned it to a precision and time in FRAM application. So it really depends on how we look at the components of the system, how we analyze the controls and feedbacks, and which category will place them from the perspective of FRAM. So this is not true. This is not that we put all of the controls in the control variable of the FRAM, where we had some feedbacks and some controls from the perspective of time and precision also in this analysis.
Thank you very much. We have another question. Assuming you use the FMV for the modeling part, how was the Monte Carlo simulation applied? Did you apply a Monte Carlo simulation to the exported data? If so, which tool could you recommend for the MCS?
For the application of Monte Carlo, as I explained, we try to use accident data with the index of the analyst elicitation. So this was one of the limitation of the study. We consider the which will be multiplied by in this Monte Carlo simulation. We considered this is based on the analyst elicitation and what the variabilities that we find out during the system. The most variable will reach the higher multiply index. So for this, as I mentioned earlier, as we use the accidental data, there might be also some areas of improvement because we need to have the real data. it was applied on realistic case studies, so we didn't have access to real data for this application of Monte Carlo simulation.
Thank you. Is there any other questions? No other questions. So thank you, Alime. Thank you very much. Thank you to IEA. Thank you everyone for joining this webinar. And please join us February 15th for the fourth presentation of this series showcasing the research results of the members of the Resilience Engineering Technical Committee. Antonio will be opening the webinar as I have a small thing to take care of. Our speaker will be Ali Caravan, and he will share his collaborative work on PSO-STPA model, a case study of an Industry 4 plant using smart glasses. Please note that attendees will receive a web link for a post-webinar survey, and an attended certificate will be delivered if you respond to the questions correctly. So I thank everyone for your attendance. Have a nice weekend and see you on next Saturday.
Thank
Bye.
you.
Thank you, Alime.
Thank you. Have a good day.
Bye.